So for students not in class today, 8.6 notes. Yesterday we talked about logarithmic equations, and today we're really going to concentrate on exponential equations. But the total objective for 8.6 is just knowing how to solve between exponential and logarithmic equations. So first off, one way to solve exponential equations is to use the property that if two powers with the same base are equal, then that means their exponents have to be equal. So, in general, if we see something exponential written down and the bases are equivalent or are the same, then that means their exponents will be the same. So let's talk about solving. How are we going to solve these type of problems? They're in exponential form, and I've got to be aware of similar numbers. So I noticed this 4 and this 8. If I did a quick factor tree of 4 and 8, I've got to figure out how can I rewrite them to be in the same base. I'm going to rewrite 4 to be 2 squared, and I'm going to rewrite 8 to be 2 cubed. So when I rewrite them, notice how 4 is being raised to the 3x, so 2 squared is going to be raised to the 3x. Notice how 8 is being raised to the x plus 1 power, so 2 cubed will be raised to the x plus 1 power. Remembering power rules, when you have a power raised to a power, we're multiplying these powers. And notice how when you multiply 3 times x plus 1, we have to distribute the 3. So now we've got this new property where, hey, I notice the bases are the same on both sides, so I'm going to set those exponents equal to each other. So we get an answer after subtracting 3x on both sides and dividing by 3, x is 1. And let's just check. This, if I plug in a 1, 3 times 1 is 3. Well, 4 to the 3rd power, we're looking at 64 when we check that. And then if I plug in 1 here, well, 1 plus 1 is 2. 8 squared is 64, so that answer does check out. Moving on to the next one, I notice I've got some bases, and I'm going to rewrite them. We already know 4 can be broken down to 2 squared, and that'll be raised to its exponent, 2x. 32, if I did a factor tree of 32, it turns into 2 to the 5th power, and then I'll raise that to the x minus 1. I'll multiply powers, getting me 2 to the 4x equals 2 to the 5x minus 5. I notice that the bases are the same, so I'm going to set those exponents equal to each other. So I'm going to subtract 5x on both sides, getting me a negative 1x equal to negative 5. Divide by a negative 1. We're looking at x equals 5. And let's just check it. On this side, we get 4 to the, well, 2 times 5 is 10, so 4 to the 10th power is 4 to the 10th power equal to 32 to the, well, 5 minus 1, 32 to the 4th power. And whenever I plug these both into my calculator, I do get 1,048,576. So another thing is when it's not convenient to write each side of the exponential equation using the same base, you can solve the equation by taking the logarithm of both sides. And we're going to take specific logarithms of both sides, because I want to make sure when I take the logarithm of both sides that it's going to be a particular base. For example, when we solve 2 to the x equals 7, when I take the log on both sides, since they're not the same base, I'm going to make sure I take log base 2 of both sides. Let's see what happens. Log base 2 of 2 to the x equals log base 2 of 7. We can use this property how log base 2 of 2 to a power undo each other, and I'm left with x equal to log base 2 of 7. And we can use change of base formula for this. Taking common log 7 divided by common log 2, which is about 2.81. We're going to do the same thing in the next example. So because I noticed 5 and 18, they won't be able to be broken down into the same base, I'm going to take the log base 5 on both sides because the base here is 5. So log base 5 of 5 to the x equals log base 5 of 18. On that left side, we can use the property log base 5 of 5 to the to the x, they undo each other. So I'm left with x equal to log base 5 of 18. And then again, change of base formula. So after using change of base, we get, this is 1.8. Next example. So what happens when we, wait a second, don't have, actually, when I say don't, when we have plus signs or minus signs, when we're adding or subtracting something within a problem, what we're going to have to do is get rid of these constants, just like we did yesterday. I'm going to have to subtract 4 on example 5 first. Once I subtract 4, now I realize, okay, I don't have the same base, so I'm going to have to take the logarithm base 10 on both sides. So log base 10 of 10, these undo each other, and I'm left with 2x minus 3 equal to, wait a second, common log is base 10, so I could just hit my calculator, common log of 17. I get about 1.30. And then I'm just going to solve this equation using my approximation. I'm going to add 3, divide by 2. We're looking at about 2.1 as an answer. We'll do the same thing in example 6. Subtract 8 first. I'm going to have to take then the log base 10 on both sides. Do change of base formula, or if it's log base 10, I would be able to just plug it into my calculator and solve for there.